welcome to the deep dive. You've pointed us toward a really interesting project today.
Yeah.
A web-based tool called the computing elevator. We've been looking through the material you sent.
Okay.
There's the web page itself, which seems to have the simulator, and the code descriptions.
Right, that's the main interface.
And also a document from the creator, a Mr. PA, explaining the whole idea behind it, the educational purpose.
Exactly. He lays out the concept pretty clearly there.
Yeah, it looks like a fascinating way to get to grips with some fundamental computer science.
Absolutely. Today we're diving deep into what the computing elevator actually is, how it visually represents, the core operations of a computer.
And why it's such a clever approach, maybe, to understanding architecture and low-level programming.
That's the plan. Our goal is to give everyone a really clear picture, hopefully, of how your computer actually executes instructions, at its most basic level, I mean.
Okay, so let's start with the central concept then. The computing elevator uses this really effective visual metaphor, doesn't it?
It really does, yeah.
You've got these twin towers.
Right.
One represents the memory that holds the program's instructions, and the other holds the data that the program uses or manipulates.
Exactly. And then there's the elevator moving between them. That's the core visual.
Right, the elevator.
That elevator's key. It symbolizes the CPU, the central processing unit, the brain of the computer.
Okay.
Its movement back and forth between the instruction tower and the data tower. It perfectly mirrors the fundamental fetch-decode-execute cycle.
Ah, that cycle, the one that happens constantly inside your computer.
Constantly, yeah.
The fetch-decode-execute cycle.
Yeah.
Can you maybe break that down just a little bit more for us?
Sure. Think of it like a three-step dance the CPU is always doing.
Okay.
First, it fetches an instruction from the instruction tower, grabs the next step.
Got it. Fetch.
Second, it decodes what that instruction means, what is it actually supposed to do.
Right.
And third, it executes it, which, might involve moving data in the elevator, doing calculations, something like that.
Yeah. Fetch, decode, execute, over and over.
Billions of times a second in your phone or laptop. It's the bedrock of all digital computation, really.
And the computing elevator lets us slow that right down, see its essence.
Exactly.
Yeah.
Slow it down, visualize it. Here's where it gets really interesting.
So beyond just seeing it, what's the real power of being able to watch this elevator in action?
Well, the power lies in making something abstract very, very concrete.
Yeah.
The computing elevator lets you see the direct link between a program's instructions and the actual movement of data.
Okay.
And to make that even more tangible, it lets you explore low-level programming yourself through a simplified set of instructions.
Ah, right. The documentation shows it uses these 1 or 2 digit denary codes, kind of like machine code.
Exactly. It gives you a taste of that basic language computers understand without, the full complexity of real machine code.
So we're talking about really fundamental commands, the kind of instructions a real CPU understands at its most basic level.
Pretty much, yeah. A simplified version of that.
The web page material, it includes a table of this instruction set. Can we look at some examples just to get a better sense of what these instructions actually tell the elevator to do?
Absolutely. Let's start with the memory and arithmetic instructions. Those are pretty fundamental.
Okay.
You'll find codes like 0x. The description says ACCE ATAX.
ACC. That's the accumulator.
Right. Think of the accumulator, the ACC, as the elevator itself. It's like a temporary holding space for the data being worked on.
Okay, so 0x tells the simulator to copy the value stored on data floor X.
Yep.
Into the accumulator, into the elevator.
Precisely. The elevator goes to the data tower, floor X, picks up the value, and holds on to it.
Got it. Load data, what about 1x?
That's ACC plus DTEX. So if the elevator is already holding a value, this instruction tells it to go to data floor X, grab that value, and add it to whatever it's currently holding.
Simple addition, very fundamental level.
Exactly. And similarly, 2x is subtraction. ACC DTEX, takes the value from floor X and subtracts it from the accumulator.
Load, add, subtract makes sense. And then there's 3x. DTEX ACC. That sounds like the reverse.
It is. That's the store operation. It takes the value currently in the accumulator, our elevator, and copies it back down to data floor X in the data tower.
So moving data back into memory. Load, operate, store.
The basic pattern, yeah.
Okay, and there's this instruction 7x. ACCET DataX plus data 9. The data 9 part looks interesting. What's happening there?
Good catch. This introduces a concept called indexed addressing.
Index addressing.
So instead of directly specifying the data floor, like 0x just goes to floor x.
Right.
Here, the actual floor is calculated. It takes the value x from the instruction itself and adds to it the value currently stored on data floor 9.
So floor 9 acts like an index, an offset.
Exactly. Think of data floor 9 as holding a special offset value. So instruction 7x doesn't just go to floor x, it goes to floor x plus whatever number is currently sitting on floor 9.
Why is that useful?
Well, this seemingly small addition is actually a really powerful concept used in real processors. It helps you efficiently work with lists or arrays of data.
How so?
Imagine you have a list of numbers stored one after another in the data tower. You could put the starting floor number in the instruction, the X part, and then use the index register floor 9 in this case to step through each number in the list. You just change the value in floor 9 instead of needing a whole new instruction for every single item.
Ah, I see. So you can loop through data more easily.
Precisely. And if the value in data floor 9 happens to be 0, then 7x just acts like 0x. It goes straight to floor x, so it's flexible.
Okay, that definitely adds a layer of sophistication.
Yeah.
Now, how do we get the program to do more than just run instructions one after the other? What about those program flow instructions?
Right, crucial point. That's where instructions like 4x, which is PCAX, come in.
PC program counter.
Exactly. The program counter basically keeps track of which instruction floor to execute next. Normally, it just increments, goes to the next floor down. But 4x lets you directly set the program counter to floor x, which means the program will jump to instruction floor x for its next step.
So what's the effect of being able to manipulate this program counter like that?
Well, it means you're not stuck going sequentially. You can skip ahead, or maybe more importantly, you can go back to an earlier instruction.
Creating loops.
Exactly. Loops, subroutines, more complex logic becomes possible.
And then there are conditional jumps, 5x and 6x.
Yep. 5x is if ACC in 0, 0, then PCX. So if the value in the accumulator, our elevator, is 0,
then jump
to instruction X. Otherwise, just continue to the next instruction as normal.
And 6x. Similar idea.
Similar, but based on negativity. If ACC 0, then PC or X, jump to instruction X if the accumulator holds a negative value.
So 0 check, negative check.
Yeah.
These are fundamental for making decisions within the program, right?
Absolutely fundamental. These conditional jumps are how you build if-then-else logic, control loops based on calculations, all that essential stuff.
Right, these are the basic building blocks. Now, there are also the input-output instructions, just 3 of them, 7, 8, and 9. What do these control?
Okay, 7, which is ACC IRL any TEPUT, is pretty straightforward. It tells the simulator to pause, get an input value from the user, you type it in, and load that value into the accumulator.
Into the elevator.
Getting data in. And 8PT, does the opposite. Takes whatever value is currently in the accumulator and displays it as output so you can see results.
Input, output, makes sense. And finally, 9, just stop E.
That's it. Halts the execution of the program, stops the elevator.
It really is amazing how much you can apparently achieve with such a limited set of commands.
It is.
The documentation even mentions, generating a Fibonacci sequence in just 9 instructions.
Yeah, that's one of the examples. It really makes you appreciate the ingenuity required in real low-level programming. Achieving complex tasks with very basic tools. You have to be efficient.
And the cool thing is, we can actually try writing and running our own little programs using these instructions right there on the simulator, can't we?
Absolutely. That's the whole point. The webpage provides that live interactive environment. You can type these 1- or 2-digit codes directly into the instruction floors and the data floors.
Okay, so let's talk about that interface itself. As detailed in the elevator1.pdf document, it's more than just the towers in the elevator, right? There are controls and things.
Definitely. Visually, yeah, you have the 2 towers, clearly labeled instructions and data, with the elevator moving between them.
And the elevator shows the accumulator value.
Yes, which is fantastic for visualization. You see the data it's currently holding right there.
And we can input our programs, like instruction by instruction, and the starting data values onto these floors, which are basically just input fields.
Correct. Each floor in both towers has an input field where you type the instruction code or the data value.
And then there are control buttons.
Right. You've got step, which executes just one instruction at a time. That's incredibly useful for debugging or just understanding the flow step by step.
Yeah, I could see that being helpful.
Then run for automatic execution, letting it go until it hits a stop or you intervene. And of course, stop to halt it manually, reset to put everything back to the start state.
Like reloading the program.
Loading the program and data, and clear to wipe the inputs clean.
There's also a speed control, normal and top speed. That's probably handy.
Yeah, normal lets you see the animation clearly. Top speeds things up if you're running a longer program or just want the result faster.
And importantly, you can load and save programs. Yeah, as JSON files.
You can, yes. Which is excellent for, saving your work, sharing it with others, or maybe for teachers to prepare exercises, collaboration, and educational uses.
And it looks like there are a bunch of preloaded examples, too, accessible via a drop-down menu. Example 1 to example 12 are listed in the docs.
Yes, those are built in. They must be really valuable for seeing different programming concepts in action without having to write them yourself first.
Definitely. And the simulator also includes, a description area?
Yeah, it explains the currently loaded program, which adds another layer of understanding, especially for those examples.
And one more visual touch as the elevator moves. The current instruction and the data being accessed are visually highlighted.
They are, yes. It makes it exceptionally clear which instruction is running and which data floor, if any, it's interacting with at that exact moment. Really helps track the execution.
Okay. We touched on addressing modes briefly with that 7x instruction, the indexed one. Can you maybe elaborate a bit more on why having these different ways to access memory is significant?
Sure. So the simulator basically supports two main modes here: direct addressing and indexed addressing.
Direct and index.
With direct addressing, like in 0x load or 3x store, the instruction directly specifies the memory location. The X tells it exactly which data floor to go to. Simple, straightforward. Indexed addressing, like we saw with 7x, provides more flexibility. It lets you calculate the address.
Using that offset from floor 9.
Right. By using a value in a specific data location, data floor 9 here as an offset, you can dynamically access different parts of memory without needing to change the instruction itself. Just change the value on floor 9.
And we said that's good for lists or arrays.
Exactly. It's a powerful technique used in real computer architectures for tasks like efficiently processing lists or blocks of data. Instead of needing a separate load instruction for each item, you can use an index in a loop to dynamically access them one by one. Much more efficient code.
That makes a lot of sense. It's like having a pointer that you can easily adjust to look at different memory locations.
Kind of, yeah. A very basic form of pointer or index.
Now, thinking about the creator, Mr. PA, he really emphasizes the educational value of the computing elevator in that second document, elevator2.pdf. What were the main learning benefits he was aiming for?
Well, his core aim, it seems, was to create an engaging and, importantly, accessible way to teach these fundamental principles. Computer architecture, low-level programming, these can be pretty abstract topics.
They definitely can be.
So the visual analogy, the towers and the elevator, that's crucial. It helps make these abstract concepts much more tangible, easier to grasp,
Yeah, actually seeing the CPU in action, moving between instructions and data, fetching and executing, that must really help solidify that fetch-decode-execute cycle in your mind.
Absolutely. And the interactive nature is key, too. It promotes active learning.
How so?
Well, you're not just passively reading about how a CPU works, are you? You're actually writing simple programs, maybe modifying the examples, and witnessing the direct impact of each instruction as it executes. That hands-on experience leads to a much deeper understanding, I think.
He also points out something interesting, that the limitations, the limited instruction set, the small memory space, actually foster creative problem solving and encourage writing efficient code. It's like being challenged to think strategically within tight constraints.
Exactly right. When you only have, say, 10 or 20 instruction slots and maybe 10 data slots and a very basic set of operations, you really have to think carefully. How can I achieve this goal using only these tools? It forces a certain kind of algorithmic thinking.
Right, you can't just throw more memory or complex libraries at the problem.
Nope. You have to be clever with what you've got. And the ability to save and share programs, as we mentioned, adds a collaborative element. Students can share solutions, teachers can give specific challenges.
And those pre-built examples sound incredibly useful for getting started. The documents mention a really wide range.
They do.
Simple counters, powers of 2, countdowns, but also more complex stuff like logical operations, not AEAD or, arithmetic routines like multiplication using addition, division using subtraction.
Yeah, even the Fibonacci sequence we talked about, and apparently a basic game example too.
That's a really diverse set to explore with such basic tools.
They are clearly designed to illustrate fundamental programming concepts in a very direct, very understandable way. By examining and running those examples, stepping through them, you can gain a practical understanding of how these basic instructions combine to perform useful, recognizable tasks.
Okay, so if someone listening is now really curious, thinking, I want to try this out, how can they get started with the computing elevator?
It's super straightforward. The website address is provided in the materials. It's https://mrpa.github.ime, that computing elevator.
Okay, mrpa.github.io.computing-elevator.
Yep. Just visit that link in your web browser. The simulator's right there on the page, ready to go. No installation needed. Just load it up and start experimenting.
Fantastic. It sounds like a genuinely valuable tool for anyone really interested in understanding the fundamental operations of a computer, not just students, maybe anyone curious.
I agree, yeah.
So to wrap up our deep dive into the computing elevator, what are the key things we should take away from this?
Well, I think the most important takeaway is that the computing elevator offers this really unique, highly visual way to understand those fundamental interactions inside a computer.
The CPU and memory working together.
Exactly. That constant interplay between the CPU, the elevator, and the memory, the towers. It beautifully demonstrates that fetch-decode-execute cycle we talked about.
Yeah.
And it introduces the core concepts of an instruction set, basic low-level programming, addressing modes, all in a manageable way.
The interactive nature, the examples, they make these often complex topics pretty accessible.
And engaging. It's actually kind of fun to watch it run, I think. And it's fascinating, isn't it, to realize that every complex application you use...
Right. Web browsers, games, spreadsheets.
That's ultimately broken down into millions upon millions of these incredibly simple instructions, similar in principle to the ones in the elevator. This tool gives you a real glimpse into that fundamental translation process.
It really does highlight that fact. Even the most sophisticated software we use every day is ultimately built upon these basic cycles and a set of instructions, just, vastly more extensive and intricate ones in reality.
Of course.
But considering the simplified model, it makes you wonder, what kind of surprisingly creative solutions might you come up with when you are faced with such fundamental limitations?
That's a great point. And it raises maybe an interesting question for you, the listener. Thinking about this basic model, how might working within constraints actually spark innovative thinking? Does having fewer options sometimes force more creative solutions?
Something to think about.
We definitely encourage you to visit the website, check it out, explore the examples, maybe even try writing a simple program yourself. What kind of challenges do you encounter? What aha moments do you have as you see those instructions being fetched, decoded, and executed by the little elevator?
Yeah, we'd be really interested to hear about your experiences if you do give it a try.